All right, here we are doing the same thing, except we are dealing with second order reactions. So we're going to be using a different integrated rate law, a second order integrated rate law, to find concentration change given time. So here's our reaction. Looks fairly complex, but we're not even worried about the chemicals here in this reaction. We just need to pull out some certain information. So they give us the rate law here. It looks a little different, but it doesn't matter. This is still a rate law. Rate is equal to K times concentration of A. It's second order, so A is to the second power, so it's second order overall. No problem. It's the same format as this. Rate, this is a rate law. Rate is equal to K times A to the second power. This is second order overall. This is a second order reaction. So even though they don't say K is equal to so-and-so, they give it to us right here in the rate law. So we can write that K is equal to, and that's a little k, lowercase k, is equal to 0.0185. And the units of K, this being a second order reaction, are m to the minus 1 times s to the minus 1. Okay. We are also given time in seconds, so that's good. It needs to be the same units as K in seconds. And let's see what else information they give us. They give us the initial concentration of our reactant here. And the initial concentration is, I'm just going to use A for short. The initial concentration of A is 1.04 molar. So we want to find what is the concentration of our reactant 380 seconds later. So same concept as the previous topic, except the overall order of this reaction is second and not first. So we just have to use a different integrated rate law. And this is the one we're going to use. In your notes, I also give you the other form of the integrated rate law that follows the line equation, y equals mx plus b. But we're going to use this one, and it will serve us just fine for these examples. Okay, so let's go to the next slide here. So the first thing we're going to do is begin by substituting K and T. And let's go ahead and get a value over here. We'll also put in this as well while we have it. So we're just going to substitute our givens, and these are all of our givens. We have K, we have T, we have initial concentration of A. So initial concentration of A is 1.04. So 1 over A, and this is not the initial concentration. This is at a specific time. There's no 0 there, okay? So we have 1 over A minus 1 over the initial concentration, which is 1.04. Okay. Now we're not going to raise this to the second power. Okay, we're not going to raise it to the second power. It is raised to the second power here in the rate law, but in the integrated rate law, we're not going to square it. Okay, we're going to use this equation, the integrated rate law, as is. So we have 1 over A minus 1 over 1.04 is equal to K, which is 0.0185, 0.0185 times the time, which is 380 seconds. Time cancels, the units of time there, seconds, cancels. And when I put this into the calculator, the value that I get here is 7.0300, and my units are molar to the minus 1. Okay. Now we have 1 over this minus 1 over 1.04, and that's molar, is equal to that value. So the next thing we can do, remember we want to isolate this by itself because we're solving for that. So let's take this and add it to this side. So we end up with 1 over A is equal to, so if I add 1 over 1.04 molar over here, it cancels out, and I'm going to add it over here. So I'll bring it here, 7.0300 plus 1 over 1.04. What do I get? Well, if I take 1 and divide it by 1.04, I get 0.9615. So 7.0300 plus 0.9615. And look, it's 1 over m, so this is m to the minus 1 as well. So they add together perfectly. See the units? They add perfectly. So when I add those two together, plus 7.03, I get 7.99. Let's take it to 1.5. We won't round it more than that. The units, that to the minus 1. I have 1 over A, the concentration of A at that specific time. So the last step, I have to invert both sides. And inverting both sides just means I'm just swapping the numerator and denominator in both cases. To explain what happens here, if I multiply both sides here by A, because I want to solve for concentration of A, but I need it in the numerator. I need it up top, right? Right now it's 1 over A. So if I multiply both sides by that, multiply this side by that as well, then I end up with 1 is equal to 7.9915 times concentration of A, right? So now let's divide both sides by 7.9915. What that gives me is 1 divided by 7.9915, and the units are m to the minus 1, is equal to concentration of A. So I've just inverted the two. You didn't even have to go through all of these steps. You could have just taken this and just flipped it. So you could just take this and flip it, put it over 1. So that'll just become A. And then you could take this and flip it, and it'll become 1 over, just like we have here. Okay? So now that I have my final setup here, we'll finish that up, where the concentration of our reactant there at this specific time is equal to 1 over 7.9915 n to the minus 1. So 1 over that is 0.125, and the units would be molar. So the concentration of A at that point, they want it to 2 significant digits, so we'll round it to 0.13 molar.